Welcome, everybody, and I'm Paul Beckwith. So I'm going to talk about climate system change from the global to the local. So the local, in this case, of course, is don't ask me to pronounce it correctly. Kragerø, Norway, and it could be really anywhere because the climate system is changing, and that changes weather patterns, of course, all over within the climate system. So if the climate background system is changing, then all weather is now occurring under our new climate system. It's hard to attribute any one particular weather event to climate change, but we are able to do that with various storms now. So my new role is the Chief Science and Technology Officer for GAIA Engineering, which is based here locally with Newt, and I work in the Laboratory for Paleoclimatology and Climatology in the Department of Geography. I'm researching abrupt climate change, both in the past, so in the paleo records, and looking at what is happening now, the system changes now, and trying to make projections for what will happen in the future. I do a lot of teaching. I've taught introductory climatology for three times. I taught in the spring of this year. I taught an oceanography course for the first time, and I've also taught geography courses in environmental issues. I have a course starting in early January, probably about 80 students, third-year students, and I'll give them I give them real life practical situations, and I'll get them to look at geoengineering. It's okay, I understand. Okay. Yeah, okay. So, can you go to the next slide, please? Okay, so I look at the climate as an overall system. And a lot of people don't do this. Like climatologists tend to specialize in one specific area, for example, glaciology or oceanography or atmospheric physics. They don't look at the overall system. So we all know that we've increased fossil fuel combustion. We've increased emissions because of our burning of fossil fuels, but also because we're changing land use. Forests are being removed for farming, etc. And this has a big impact on how much CO2 is in the atmosphere. So the greenhouse gas concentrations are way up, and this is for CO2, CH4, which is methane, is a big one, and nitrous oxide, N2O. So we all hear of this, from Paris, 2 degrees global average temperature. We can't go higher. The big thing out of Paris was that 1.5 degrees Celsius is probably the safer limit. We've already passed 1 degree Celsius. But the thing that people don't really talk about is it's the distribution of the temperature on the planet that is more important. So the Arctic is warming the high Arctic 5 to 8 times faster than the global average temperature. And this is because the Arctic is getting darker. We're losing sea ice, and when we lose a white sea ice, it's replaced by dark ocean underneath. We're losing snow cover on the land, mostly in the spring, and when there's less snow cover, there's the dark surfaces of the permafrost and tundra underneath. So the Arctic is getting darker. So in the summers, when the sun is, there for 24 hours a day in the high Arctic, then there's a lot more absorption of the sunlight. Instead of being reflected from a white surface, it's absorbed by a dark surface. It's causing warming. So the additional solar absorption is warming the Arctic. So what does this do? So it's the sea ice snow cover. Greenland's also getting a lot darker. As the surface ice melts on Greenland, then you get all the dust and dirt that's being collected in the ice, and it gets concentrated as the ice melts. So what does this do? How does this affect this? I have a saying. First said it a couple of years ago. Many people have used it, but I'm the original one. What happens in the Arctic doesn't stay in the Arctic. So the Arctic is not like Las Vegas. Okay, so The Arctic, because the Arctic is warming much faster than the equator temperature doesn't change. We know that. If you live on the equator, the yearly temperature variation might be 3-4 degrees Celsius all year. It doesn't change that too much because it's getting 12 hours of sunlight year round. So it doesn't really have the seasons that we have. As you go to the farther away from the equator, then you get more seasonality, as we know in the north. So what happens is when the Arctic is warming extremely fast, and the equator doesn't change much, the temperature difference from the Arctic to the equator is greatly reduced. And why is this important? This is important because the heat, the equator is hot, the pole's cold, the heat wants to move from hot to cold, so it does that in the atmosphere, and it does that in the oceans. About 2/3 of the heat is carried in the atmosphere, about 1/3 in the oceans. So in the atmosphere, there's less heat being carried. So what happens is the jet streams, which guide weather patterns, and they kind of act as a wall between cold, dry Arctic air and warm, humid southern air. Those jet streams slow down and they become wavier and they become kind of stuck in place. And so we get more extreme weather events because the moving jet streams guide storms. So because it's warmer overall, there's more water vapor in the atmosphere. And when that water vapor rises and condenses into clouds, it releases energy, and that energy fuels storms, it fuels extreme weather storms. So the more water vapor, the more intense the storm. We all know that, the hurricane is tremendous amounts of water vapor. So these storms, as they move across the land, if they're moving more slowly, then they're depositing more precipitation in one particular area, and they don't reach areas where they would have reached before. So we get many cases where there's torrential rain events. We get 3, 4, 5, 6 months of rain in one night or two, and it floods out a city or an area. We're seeing this all over the planet now. And we're also seeing more frequent events. So the frequency, the intensity, the strength, and the duration of these storms is increasing. We're also seeing storms occurring where they never happened before. We're seeing things like tropical storms or even hurricanes hitting the Middle East, for example. We're seeing weather events being sort of out of kilter or whiplash, changing from extreme amounts of precipitation to extreme drought and so on. We're seeing massive droughts in other places like California. It's been ongoing for over 5 years. And that affects the food supply, the supply of vegetables. California is kind of the breadbasket for fruits and vegetables in the U.S. Also in South America, the São Paulo droughts and so on. So the atmosphere is changing. The weather patterns are changing because the Arctic the root cause is the warming in the Arctic. The oceans are also changing, and this is a new thing just in the last few years. So the ocean currents, such as the Gulf Stream, are actually being reported to be slowing down. And in fact, in 2009, 2010, the data indicated that the Gulf Stream basically shut down for a while. And scientists didn't believe the data, but there was a paper just within the last 6 months or something that looked at sea level rise off of the U.S. coast and found that in that time period, 2009, 2010, sea levels rose 5 inches off the 5 inches, so about multiplied by 2.5, so 12, 13 centimeters sea level rose off of the U.S. coast, east coast, north of New York, all the way up into Maine. And it did that because the Gulf Stream will normally come up off the coast and veer across the Atlantic towards Europe, feeding Europe. But because it was going slower, it overran. It didn't curve as much. It overran the continental shelf off the U.S., greatly warming the water there and causing sea level rise in that period of time. So the Gulf Stream then picked up again after that, and the sea level sort of stabilized. But we're getting these type of things that we didn't expect. Nobody expected this. but I think we need to become more aware that we're going to get a lot more of these types of things slowing down, move forward. It all depends on the sea ice, how quickly the sea ice declines. Also, south of Greenland, there's this cold blob of water. Now, I interviewed Jason Bach, who's an eminent glaciologist who does a lot of work on Greenland, and all of the climatologists in the climate science community knows Jason Bach. And he thought that the cold blob south of Greenland is because of increased melt from Greenland, which would cause fresh water to move off Greenland and into the Atlantic, and it's lighter than salty water, so it would float on top and then maybe cause this cold water pool. But I think the main reason is that the Gulf Stream is slowing down. It's not moving as far north as it was, it's moving further south. So where the Gulf Stream is now moving, the water is warmer than normal, and where the Gulf Stream used to be, the water is colder than normal, because it's a warm water current. And so I think that it's probably a combination of reasons. So next slide. Okay, so it's not just so the Arctic changes are affecting the entire northern hemisphere. I hope I've demonstrated that. But so what happens? Well, there's extra heat at the equator, right? If normally heat will always move from hot areas to cold areas. So if the Arctic is very cold, heat will move from the equator northward, like I said, in the ocean and in the atmosphere. But now the Arctic is warming because it's absorbing more sunlight. So there's less requirement. There's less heat that is going to move from the equator northward. So what happens to that extra heat at the equator? Well, two things can happen. It will evaporate more seawater at the equator, causing more clouds. So it can do that, or it's going to be transported to the southern hemisphere. So there'll be an increase in heat transported to the southern hemisphere, both in the atmosphere and the ocean. So so both of these things are occurring. So the additional evaporation of the water means that there's more water vapor in the air at the equator. So that will lead to more clouds. And we call those clouds the intertropical convergence zone. And that zone of cloud, if you look at a satellite image of the Earth, you can see a zone of clouds around the equator, and it moves north and south depending on the season. But there'll be more clouds there. That's one factor. The second factor is there's more heat moving southward. So that heat gets to Australia. So we're getting massive heat waves in Australia in the southern hemisphere summers is one thing. But also Antarctica is very cold. It's like a huge, massive cold region that has its own climate in a way. So the heat gets down to southern Australia. So there's a large temperature difference between around southern Australia and Antarctica. And that large temperature difference causes the jet streams to move faster there. And because the jet streams are moving faster, they're strengthening. They become less wavy. And because of what's called the Coriolis force, they will pull sea ice that has formed around Antarctica further away from the continent. So the Antarctica sea ice is rising 1.5% per decade. And, of course, climate change deniers jump on that and say, well, the Arctic is losing all this ice, but Antarctica is gaining ice. This is the reason, because of the climate system. So this is not a good thing. It doesn't, you can't just jump on one thing. But, it can be explained if you look at the overall climate system. This hasn't been published. This is it just has to make sense. It'll be published. Somebody will study it and publish it, and probably within a year. The physics of the system, the overall system, means that this has to happen. There's no other alternative. So the ocean currents are also changing around Antarctica, and the ocean currents are going underneath the extra sea ice, and they're warm, and they go right under, and they attack the ice. They melt the ice of the glacial ice on Antarctica from underneath. A lot of the ice is sitting on bedrock that is up to a mile or more. That is several kilometers underneath the ocean. It's sitting on there, and it's being melted from below. Next slide, please. So the Arctic, the massive changes in the Arctic, I think, are nonlinear, and they are. It all boils down to how long will the sea ice stick around, because as the sea ice vanishes, more and more of it vanishes, and the snow cover vanishes, and then these effects I'm talking about will be amplified. So I'll talk more about that in a minute. So this is a very good site. Actually, I think we'll switch. I want to switch and show you a few websites, and then we'll come back to this, because any of you can go onto the internet and can access the data that I'm going to be showing you. So let me go to the computer. Okay, so if you Google climate reanalyzer, okay, there's 4 websites that are all you really need to become your own climatologist. So I'm going to show you how to do that right now, and weather person. So Google climate reanalyzer. This is what you get. You get this website, and there's all these menus here. So let's see what's happening in today's weather, for example. Okay, so you get today's weather. So this is temperature here. You know, the scale is on the right-hand side of the temperature, Fahrenheit and Celsius. And what you can do is move the mouse over, and you can click on the Earth, and you can get any view from all over. You know, it moves around. So there's North America here, Antarctica, and this gives the temperature and the color scale. So you can tell what the temperature is. So look at over North America. You know, it's warm here, all the way up here. But how do you find out how warm it is? Well, the temperature anomaly, and look at the day, by the way. This is data from this yesterday. And there's some numbers down here. You can actually get this view of the Earth instead if you prefer with the temperature scale here. So let's have a look at temperature anomaly, which is how far the temperature on the land is different from normal. So you can see what's going on in Canada right now. The East Coast is extremely warm. I was told Ottawa hit 14 degrees Celsius yesterday, and the daily lows are about 8 degrees. Normally, Ottawa should be -5 degrees Celsius. So it's 20 degrees Celsius warmer than normal. You know, this ugly patch here. And you can relate these patches of warm air and cold air to where the jet streams are, which I was talking about a bit earlier. So if I click on this, you know, that you can see other parts of the planet. You can see very warm areas here and so on. Okay, so you can get all the different views here. And now the next thing is sea surface temperature. You know, these are very artistic. I mean, you could, you know, generate some nice, you know, posters or something from the different colors. There's a lot of artistic interest in these. So let's, rather than temperature, let's look at the anomaly, which is the difference from, that would be what it would do is it would take the last 30 years of data on this particular day, Monday, December 14th, to get the average temperature of the water on the surface, and it would get yesterday's temperature on the surface. It would subtract from the average, and that gives you an anomaly or a difference. So what we're looking at here, you can see the Gulf Stream here is very warm, and then there's some cold blobs here. This is the cold pool south of Greenland that I was talking about. And what you can see in the Pacific is this is the El Nino for this year. So this is the largest El Nino that we've seen ever. This is much stronger than the 1997 El Nino, which was the record holder, the largest of the previous century. So this year it's much worse. Now they're much stronger. So what happens is the trade winds normally blow from east to west. So the winds are normally blowing this way, and the warm water is piled up over here. Then the El Nino phenomena is those trade winds relax and even reverse direction, and this warm water sloshes all the way across the Pacific, comes to South America, and creates this warm water, and then that affects global climate. What we're seeing, you can see warm water here, and this has been here for a long time. This feature has been here for a while, and up to recently there was a very warm water pool here, which basically the jet streams coming across, they couldn't go right through the warm pool, they'd have to go either north or south. So you can see, there's lots of other neat things here. You can see precipitation and clouds coming across. You can see precipitable water, how much water is in the atmosphere. And this is the jet stream. So the jet stream winds, there we go. This is the jet stream. So you can see these jet streams. They're coming down here, coming here. And the speed of the jet streams is in red. So last winter, it was interesting because we had record velocities of the jet streams coming across from North America to Europe. So there was a commercial airliner, I don't know, 777 or something. It had a record minimum time going from New York to London. And its average speed over the ground was something like, almost about 900 kilometers an hour. I mean, the plane would do, 600 or 700 kilometers an hour, but the jet streams it was traveling in were going 300 kilometers an hour. So it carried it across, with record time. So we're seeing lots of, also we've had terrible weather in parts of Europe. We had a 1 in 200 year flood in parts of Norway. Parts of England were flooded out. There was massive wave size that's been eroding lots of the UK. And this is because the wind patterns are shifting and the wave patterns are shifting and so on. So this is a great site, Climate Reanalyzer, but this is even better. Okay, this site is, if you Google Earth Null School, it's a funny name, N-U-L-L School, then it brings up this. And if you put what we're looking at, if you wonder what we're looking at, well, this is, if you click here, you can see the green circle, that indicates the data. So it gives longitude, latitude. It gives 3.5 degrees Celsius. So this is sea surface temperature anomaly, similar to the previous one. And you can just drag this to wherever you want to go. And you can use the mouse to, so if we go up to Norway, for example, see how much, just my geography here. And then expand, you can use the slider to expand it, and then you let it sit for a bit. And you can see the water temperature around Norway. And you can click on a region, and it tells you the anomaly relative to normal. There's loads of stuff you can click. If you click on Earth, it brings up these menus. So you can get ocean, air, ocean, chemistry properties, particulate matter. You can get sea surface temperature, anomalies. If I click on air, then these are different. This is the surface. This is near the surface. You can go up to, these are different pressures. The jet streams are up about 250 hectopascals of pressure. So I can click on that and it will update. So if I click back on Earth again, then these are the jet streams. So let's go out a bit. And let's go to the Arctic. And so you can see these are the jet streams that are moving around the planet. So here it's splitting, and then it's recombining and so on. And if you just click on a region, it's 291 kilometers an hour there. So if you play around this from time to time, you get kind of a feel for what's happening on the planet, what the Earth is doing. So this is an excellent website as well. Now, I said that the Arctic is the key to global climate. That's certainly happening now because of the Arctic warming much faster. So there's everything you want to know about Arctic is on this site, Arctic sea ice. So there's images of ice concentrations here from various research places. This data is it's almost real-time data. It's data from yesterday or even this morning. You can see how the Arctic sea ice is changing over time, what it's done previous years. There's all kinds of stuff here. This is another great site to play with. And this is U.S. military data on how the ice is moving. So the scale here is in centimeters per second, up to 30 centimeters per second. The red area is the ice is moving very fast. So what's happening now is You can play a movie, say, if I click on this, then you can play a movie, like you can play the last 12 months. So let's just do one here. Ice thickness over the last 12 months. So there's the date up here, January 2015, into February. Now the ice, this is thick ice is black, red, this is in meters, thickness of ice. So you can see that there's only thick ice here. This ice here is very thin, it's between 2 and 2.5 meters. You can also see what happens over time, like you can see some of the thick ice is being exported. So if the wind patterns are circulating like this, then a lot of this thick ice will be exported out. This should all be green and yellow. Okay, so we've reached a state of sea ice where it's a lot thinner, and it's on its way out. We're heading to an ice-free Arctic. It's just a matter of when. I'll talk a bit more about that in a minute. This is, if you go, out boating or something, onto the ocean, and you're always worried about weather, storms coming up. So this is a great site. Just Google Wonder Map. It's part of the Wonderground, which is Weather Underground. A meteorologist, well-known meteorologist, created this site and does this full time. It's a very successful site, and he created something called the Wonder Map. And you can use the slider of the mouse to zoom in, or you can zoom out, and you can play movies of the weather. So there's no weather. I mean, it's very clear right now. There's no clouds or anything. But if I go back out a lot, just so you can see there are some things happening somewhere else. It takes a minute to refresh. And you can see there's still not much going on. If I go out a little bit more, here we go. We've got some stuff going on in the UK. So you can move this around. You can go to any location in the world, and you can play a movie. So, for example, if you're in the United Kingdom somewhere and you want to see how long does it take this to reach me, you can, zero in, focus in on the region. You can do the movie and see how the storm clouds have moved in the last hour, and you can say, well, it's moved about half the distance to me in an hour. So in another hour, it's going to start raining where I am. And I tried this on the roof of my house. I really zoomed in. I've got a deck up there. And I said, okay, it's going to start raining in about 11 minutes. And sure enough, it started raining in about 11 or 12 minutes. So you can actually do this. You can use this, and it's on your smartphone when you're out in the boat. You can do much better than any weatherman or weather person with this site. Okay, so can you go back? Okay, so there's loads of data, there's loads of websites. There's loads of resources on the web, and with smartphones and cellular technology, you can get this information wherever you are, pretty much. Okay, so next slide. So this is the weather. This is Climate Reanalyzer. Next slide. Okay, so I told you I look at the overall climate system. So, what do I mean by that? I mean, most people think of the atmosphere, controlling the weather, and then long-term averages of weather being climate. But it involves the oceans, interactions with the ocean, interactions with the biosphere, interactions with the earth, with the lithosphere, interactions with, soils, especially if you're looking at carbon, like where does carbon go? How does carbon get into the atmosphere? And there's a dynamic balance always going on, but what humans have done since the Industrial Revolution is we've upset the balance with carbon. Right? We've converted carbon that's stored deep in the earth, and we put it into the atmosphere and ocean. So we've changed the chemistry of the atmosphere. Right? We've also changed the chemistry of the oceans. Right? We've changed the pH of the oceans. So we need to slash emit. So I think of the climate solutions, and I gave this presentation in Paris, and I'll talk about Paris in a few minutes. So I'll go through the slides a bit quickly, because I want to leave lots of time open for questions and so on. I can give you my general impressions of Paris and also what I think of the agreement and so on. But we also have the cryosphere with the ice sheets and so on. So we've got this climate system, and there's a balance, and we've kind of tipped the balance too far one way, so we need to look at how we bring it back So slashing emissions is just one thing that needs to be done. And I'll talk about what some of the other things are in a minute. So next slide, please. Okay, so this is data from ice cores. The ice cores in Antarctica in particular. So the ice contains a record or a proxy of previous climate. We can count. The ice is snow builds up on the surface and then it's compressed as more snow builds up. And eventually, the weight of the snow above compresses the ice enough so that the snow enough so that it converts into ice. And that ice will trap bubbles. And those bubbles are the composition of the atmosphere when the bubbles were closed off and they were no longer connected to the atmosphere. So we can measure as we go deeper and deeper. We can date how long ago that ice was laid down to get a time period. We can also measure the amount of the composition of the air bubbles to know what the atmosphere was like at a certain time, and we can measure isotopes of oxygen-inducing chemistry to determine what the temperature was at a given time. So we get a temperature and a gas composition. So this is this shows the this is the atmospheric methane up here and the CO2. So the CO2 varies between about 180 and 280 parts per million for the last 800,000 years. Actually, the ice core is going to take us back to 1 million years, probably the new ice cores. And so the CO2 is in a compact range, and right now we've gone way off scale. And this started at the beginning of the Industrial Revolution. And the methane is even higher, gone off even higher scale. Methane varied from about 350 to 700 parts per billion, and now it's well over 1,800. In fact, in parts of the Arctic, we're measuring readings of 2,500 parts per billion. Okay, so we've changed the chemistry of the atmosphere. We've changed the nature of how the atmosphere absorbs solar radiation, which is coming up from the Earth, infrared radiation. Okay, next slide. So this shows it's the rate. This is a closer time scale, 85 to roughly now, and you can see the fluctuations. And it's kind of pulsing because what happens is most of the vegetation on the planet is in the northern hemisphere. So when we have a northern hemisphere winter, the deciduous trees have all lost their leaves, so they're pretty dormant. Come the spring, the buds come out, the leaves start growing, they suck CO2 out of the atmosphere. So those drops that you see, those dips, are when the northern hemisphere deciduous trees and plants are all starting to grow. And then in the fall, when the leaves drop and they start going dormant and it gets colder, then we get the rise of CO2, less CO2 is being absorbed. So, but you can see this is the increase per year. You can see it's trending up. And this is the methane. It trended down for a while, but it's rising up again. So the what's happening? Well, we don't have a choice at this stage. I think the world is starting to recognize that we have to do something about emissions. That's what the whole idea of the Paris conference, to put a global cap on emissions, reduce emissions. So they were actually talking about, in order to stay under the 2-degree window, we need to go to zero CO2 emissions by about 2050. And that would require a drop of something like 8% a year. And if we want to stay below the 1.5-degree window, we need to drop zero emissions by 2030. Now, there are other things that we need to do. I consider zeroing emissions. I'll talk about it now. Okay, you have a bar stool. There's 3 legs on the bar stool. Okay, one of the legs is zeroing CO2 emissions. And that's all we've been talking about at Paris. Okay, but from my work and the work of many other people, there's 2 other things. There's 2 other legs on the bar stool. It won't balance just on one leg. The second leg is carbon dioxide removal. What we can do is we can help nature extract more CO2 from the atmosphere. we can sort of nudge it along to extract more CO2 from the atmosphere. I can talk a bit more about some of those methods, but in general, they're called carbon dioxide removal methods. For example, one of the limiting factors in the ocean for plankton, phytoplankton, is they're always at the surface because they need light, but they also need nutrients. So if they're on a coastline where water is upwelling, nutrients are plentiful in cold water that's deep down. So if that cold water is coming up at a coastline, sort of upwelling, then it provides the nutrients. You get phytoplankton blooms, and you get tremendous growth in marine life, and all the way up the food chain, you get creatures. If you're in the middle of the Pacific and there's no upwelling and the water's warm, so it's stratified, there's no nutrients. So you don't, it's like a desert in the ocean. There's no marine creatures in the surface water. So if somehow you could bring cold water up from below, and there's some methods, the engineering methods to perhaps do that, then you can get phytoplankton blooms and tremendous growth. So you're helping nature. And when you have phytoplankton, it's based on carbon, and then as it dies, it sinks to the bottom, or it's eaten by fish that then excrete. Then that waste goes to the bottom, and the carbon then goes into the sediment on the seafloor. So it's called a biological pump, and you can enhance that. So that's the second leg of the stool, carbon dioxide removal. There's about a dozen high-tech companies that are looking at ways to extract CO2 directly from the atmosphere, like artificial trees, things like that. There's ways to, there's something called biochar, which is, if you take organic matter in the ground, then when it decomposes, it produces CO2 and or methane, depending on how much oxygen is available. If you heat up that organic material in the absence of oxygen, it's called pyrolyze it, you can form this material called biochar. It's like charcoal. And if you put it in soil, it increases the fertility of the soil, so it helps plant growth, and it also stores CO2. It's a very stable form of carbon storage. So people are looking at, there's all kinds of, I could go on the whole talk about CDR methods, but that's the second leg of the stool. Now the third leg of the stool is, it looks to, if you look at the trend of sea ice, it's heading to zero. It could reach zero almost by 2020 or even earlier. So we'll have a blue ocean event. We'll have no ice in the Arctic Ocean at the end of the summer melt season. And if we allow that to happen, then the melt rates from Greenland will go way up, causing sea level rise to greatly increase, where we'll increase emissions of methane from seafloor and from the permafrost. It's been estimated that if the average temperature over the Siberian and Alaskan and Canadian permafrost in the north exceeds 1.5 degrees above pre-industrial, then that will cause tremendous releases of methane. We're already seeing things that we didn't expect. We're seeing these holes in Siberia, blowholes, where clath rates, methane clath rates deep under in the ground are thawing. So it expands, the gas expands about 200 times, builds up pressure under the ground, and then eventually builds up and blows a big hole in the surface. We're seeing this in Siberia. In fact, some planes that are flying over that region are seeing this all over the permafrost there. And this is a large increase in methane emissions. And it's also a recent paper just in the last few weeks is seeing a similar thing in the Kara Sea on the seafloor. So just on the seafloor off Siberia, we're seeing these features on the ocean floor where there's mounds that are being pushed up by methane. And if you consider back in the paleo record what happened long ago, off New Zealand, for example, there's pockets on the seafloor, or features on the seafloor that are, some of them are 50, 100 kilometers in diameter, and it looks like there was a massive release of methane which had a global change of climate. We've seen the climate of the Earth is, we're used to stability. We're used to linear changes, slow changes. Now, it takes time, but the climate doesn't really work like that. We just happen to be in a nice, friendly regime of climate, and the risk is that we take it out of that. That we already are well on our way to taking it out of that into nonlinear climate behavior. So the global average temperature on the planet has risen about 5 or 6 degrees in a decade or two, many times in the past. So we talk about 2 degree cap or 1.5 degree cap. we're kind of being hopeful there. We're not getting the full story because we're risking a very large, abrupt, rapid change if methane comes out big time from the Arctic. So I'm in a group called the Arctic Methane Emergency Group, and we've been studying this for about 5 years, and we've come to the conclusion about 3 or 4 years ago, that we need to look at ways of cooling the Arctic to keep the methane in place, to keep the sea ice and snow cover there, so that we still have a recognizable weather system. Because if we lose sea ice and we have this blue ocean event, and the weather extremes that we see now, the increases in frequency, severity, and duration of extreme weather events, they'll increase about at least an order of magnitude 10 or 20 times. So we're seeing the tip of the iceberg in terms of extreme weather, and you can see with 1 degree of warming what's already happening with damage to infrastructure, droughts and floods and all of this. So this will get much worse. Okay, so the next slide. Okay, so this just shows, we have lots of data. There's lots of images like this. In fact, a new one just came out today. I communicate a lot of this stuff via Facebook. So I have a Facebook page, and Twitter, a Twitter account, and also I have a new website called Paul Beckwith.net, and I have all kinds of videos. I try to educate people. I try to be completely open with what I know about the climate and communicate it. I look at communicating it through blogs and tweets and Facebook posts, and this is how Nude actually came across and found me and asked me to come out to Norway because of some of the social media stuff. And when I was in Paris, I had all kinds of images and pictures and stuff and information posted on Paris, like the videos of the top climate people and so on. So this stuff is coming out. But this is what I mean. The Arctic is warm. So this is the change of temperature from 1960 to 2009, and the Arctic is all red. And the red is 2 to 4 degrees warming. Right? The equator doesn't change much. So when we talk about a 2-degree temperature rise globally, or 1.5 degrees, what does that really mean? I mean, this is the number for the overall rise, 0.66. But you can see that different parts of the Earth are greatly affected different ways. And because the Arctic is warming so fast, this is the, if you take the average across all longitudes at a given latitude, then the Arctic is 2.4 degrees, right? Compare 2.4 to 0.66, that's a factor of 4. Now, I just saw this graph and posted it on Facebook and sent it on Twitter. It came out for November of this year. And this number for November of this year is 1.05. Okay, so this November, this past, is 1.05 degrees warmer than the average over the last 30 years. Okay, so we talk about 1.5 degrees global. Well, we're already at 1.05 this year. Now, this year, compared to previous years, we're about 0.2 degrees higher this year than previous year. And if you look at the data, all the other years are like coming across, and we're up here. Okay, now hopefully that will go back. Hopefully this is an El Nino year. It probably will. Right? The El Nino year, tremendous amounts of heat are coming out of the ocean. We haven't had a strong El Nino for a while, so the ocean stored that heat, and it's all coming out this year. But then that should shut off, and it will go back. But there's some people that are talking about having more persistent El Ninos, or reaching almost like an El Nino state, a permanent state. I don't think it's going to happen. I mean, the El Nino's been going on for thousands of years. But we are really playing with fire. We're in an unknown area. I mean, the air we breathe right now the chemistry is different from what all previous humans have breathed. In fact, you have to go back millions of years to have it different. Okay, next slide. Okay, so also the change in temperature on the Earth, it varies with the seasons, of course. So this is December, January, February. Okay, so this is winter, spring, summer, and fall. So what what you can see is the bright red in the Arctic is mostly in the winter and in the fall. Okay, so summers aren't that different, right? There's some difference, but most of the heating that we're seeing in the Arctic is going on in the winter and the fall. Okay, next slide. Okay, so the IPCC, so basically these events in Paris. Last year it was in Lima, Peru. Next year is in Morocco. These events are called COPs, or Conference of the Parties. The countries are called the parties, and there's about almost 200 in the world. Right? I think there's 196 or something. So all of these COPs are the meetings, the conference of all these parties or countries. And 21 is the 21st COP. So we've had 20 COP. We've had 20 previous ones. Lima was number 20. And emissions are rising faster than ever. So for anybody to say that there was any success in these COPs in the past would be fooling themselves, right? 20 COPs in squad, that's what I say. So lucky 21, you know, if you play blackjack, maybe lucky 21. So 21, I would argue that 21 is a very important and key success for humanity, as long as we follow through on things that are promised. I think the COP in Paris, the agreement, got the ball rolling. If you haven't seen John Kerry's speech a couple days before the end of the COP, make sure you watch it. He was talking about lots of the things that I'm talking about. He was talking about the threat to national security, about the threat to global food supply, about the connection between climate change and the trouble in the Middle East, the migration, the Syria issue. Because what happened is in Syria from 2006 to 2010, they had one of their worst droughts on record. It wiped out the farming industry, and about half the country relies on farming for employment. So 1.5 million people moved from the rural areas of Syria into the cities, and then they didn't have jobs there, and then it caused the unrest, and it built up from there. But the root cause was the massive drought and the loss of livelihoods of 1.5 million people in rural areas. So as we get more and more extreme weather events, we're going to get more and more, there's more and more geopolitical repercussions. So the sea ice, the IPCC report that the policymakers go on is based on these computer models, the average of which is the black line, and the variation between the models is these lines, and there's about 24 odd models, something like that. The observations are showing a completely different story, right? They're dropping off here, right? So how can we base global policy on this when the system is behaving a lot faster? And how can we possibly be doing the right thing to have an IPCC report out every 7 years on the state of the climate when the climate is changing very rapidly? It just doesn't make sense to do that, but yet that's what we're doing. But I think more and more countries and world leaders and people you hear the word abrupt climate change more and more often. Like people have some feeling that there's just something wrong with the climate. You know, there's something wrong, and then it will affect everything. I mean, the wildlife on the planet is migrating, right? Certain species like a certain temperature range and certain precipitation range, and if the temperature range is shifting too high, they're not comfortable, so they migrate closer to the poles where it's colder to get the environment that they're used to. So that we're seeing a massive migration of species, animal species, and the same with plants. I mean, the seeds are blown, and we're seeing areas where forests are changing into grasslands, for example, if there's not enough water to support the forest. So if there's not enough water to support a forest, and the trees get weakened, there's pestilence that weakens them more, like pine beetle and emerald ash borer, and then there's a forest fire, the forest burns down, and the forest doesn't grow there, right? We get grasslands instead because the climate has shifted. So, we're having very rapid shifts. Like there's a region in northern Siberia that's just tundra, and come across in tundra, and it's so warm there that the tundra has frozen, so now there's the soil there, and there used to be just grasslands and shrubs a decade ago, and now there's forest, larch and birch, 6 to 8 foot high trees. There's a whole forest there, and this is in a decade, or less than a decade. So we're also seeing, I call it real-time evolution. We're seeing some species that have very short reproductive cycles. They're changing. Their behavior is changing. They're basically undergoing almost real-time evolution as they struggle to survive the rapidly changing climate. If things change slowly, great. But the changes that we're seeing now are probably at least 10 or 15 or 20 times faster than the rate of change we've had in the previous geological record. So what we're doing now is much faster, at least by 10 or 20 times than anything that the Earth has experienced in the past. Okay, so next slide. I don't want to keep going. I want to talk more on Paris in a few minutes. So this is just showing another view of the sea ice. And okay, so this heads to zero, right? It heads down to zero. And I have this in a better slide to follow, so you can advance. Okay, so the data is showing, the trend is showing the sea ice heading to zero in almost an exponential pattern. Now, I talk about a blue ocean event, and that's if the sea ice volume goes to zero, or essentially zero. By zero, there might be some ice that's stuck on the land around the Arctic. It'll go to below about 1 million square kilometers at the end of the melt season. When will this happen? Well, if you just look at the graph, you can show that. I can show this to, a few years ago, I showed this to my, 8-year-old kid and said, where does this go to zero? And they come up and they see the graph go down, and they say it goes to zero there, about 2020 or before. You show this to one of the world top scientists in climate change. Where does this graph go? They won't say it goes to zero there. They say, well, there's probably feedbacks. There might be negative feedbacks. The graph will probably curve around. We can't say it goes to zero there. Like, that seems a bit ridiculous to me. But, 2020 or earlier. I mean, there was actually a Canadian Environment Canada scientist who said 2020 to 2040. The IPCC, the Paris policy people base their work on, say 2040 to 2060. I think in the last report by the Intergovernmental Panel on Climate Change, they said 2060 to 2070. Right? Well, I mean, this curve doesn't look like it's gonna, flatten out, or it looks like it's going to zero, pretty soon. So we have to be prepared for that. Okay, so next slide. You can skip that one. I'm going to skip a bunch. I want to get to the end of it. Okay, yeah. So this is a more recent one, and there's all these different curves of where it could go. And so this was 2012. It went really low, and then it went back up again. And this year it's gone back low. But the trend is still a lot of these curves go to zero before 2020. So we're heading to where, if we think extreme weather events are bad now, if this curve goes to zero, we're going to get a great increase in extreme weather events around the world. Okay, next slide. This is all of the different months. So when the sea ice is really thin and there's not much left at the end of the summer, then it refreezes as the season changes. But if there's the ocean water is warm, if there's not much sea ice, then it takes a lot longer to refreeze. So the next year, there's that refreeze is not very good. There's less of it. Also, if there's less ice, then on the outskirts of the ice, there's more wave action. There's more wind over the water, which causes waves, which breaks up the ice more. Just go. I'll do a few more slides, and then we'll break for questions, I think. So go ahead. You can advance. Okay, yeah, I'll just show 2 more slides. So so here's a scenario that I see as possible. If the overall trend continues, we'll have our blue ocean event by 2020. Now maybe, if we get, it depends a bit from year to year on weather conditions, but the first year when we have no sea ice, it'll probably be centered, usually the minimum is about mid-September, so there'll be no ice, say, for a couple weeks, bracketing September 15th, or maybe 2 weeks before, 2 weeks after, so open, and then it will start reforming. If that happens, it's likely that within a year or two later, that duration of open water would be 2 or 3 months, and extended to 5 months by about 3 years on after the initial blue ocean event. And then roughly it would head to being open year-round by about 10 years beyond that, 2030. Now, if the ocean is open in the Arctic year-round, we're obviously in a much warmer climate. We've actually gone through an abrupt climate shift. And then the amount of heat there would, then the melt rates on Greenland would obviously greatly increase, levels would greatly increase, and so on. So there's a lot of feedback in the system. So I would argue that we can't allow this to happen. Okay, that we have to treat this as a three-legged stool. We have to zero emissions as soon as possible, but we also need to remove CO2 from the atmosphere, and we need to look at ways to cool the Arctic. And we know some ways that will do that, but they're very controversial. People don't want to hear them. So I went to Lima last year. I was in the first COP that I went to was in Lima last year. So I was involved in a lot of press conferences talking about the climate system changes, talking about methane coming up in the Arctic, talking about jet stream changes and how quickly Greenland and Antarctica were melting and so on. Talking about how the IPCC process needs to be revamped. We need updated science reports every year on how the climate has changed, because we're seeing things happen, on a month-to-month, almost day-to-day basis in the climate. We need to communicate these changes to the public and explain, these extreme weather events are just not, they're not an act of God. They're because we change the chemistry of the atmosphere, the oceans, the way the heat moves, and at least get people a basic enough understanding to realize that, that what we've done, why it's occurring, and what we can do, beyond just slashing emissions, which was all talked about in Paris. So, Paris was a great. I'm hopeful about Paris. You're going to see lots of stuff about Paris in the news. You're going to see the whole spectrum of things, and it's already there. I mean, I just looked today for a while. People saying Paris was a complete failure, will do absolutely nothing for the planet. To Paris was an incredible success. It gets the ball rolling. It's going to cause global investments of trillions of dollars. But we need to, hold countries to their promises. And the thing is if you develop a technology, if somebody developed a cheap technology to remove CO2 from the atmosphere, then bang, we start removing it at very fast rates. In fact, if we had this ideal technology that could remove it faster than we burned fossil fuels and emitted it, then we could lower the concentrations in the atmosphere. We would also have to look at ways that would over time would bring us back to where we were before with a colder Arctic. But that's not going to happen right away, so we need to look at ways of doing other things. So the point is, I think I'm very hopeful from Paris, because it does get the ball rolling. I mean, you had people like Pope talking about the necessity every year on how the climate. John Kerry's speech a couple of days before the end. The U.S. government recognized it. I mean, it's a huge economic threat, climate change. It's a huge threat to human health. It's a huge threat to global food supply. It affects everything. So, when we run businesses, when we do things, we need to consider, how much carbon is involved. We need to consider, climate as a part of it, and just move on and get things done. No more talking. I mean, the idea of 40,000 people going to Paris, do we really need that? I mean, I thought people so scientists are even of mixed views. James Hansen said Paris was a huge fraud. He's one of the top climatologists. He testified in 1988 to the U.S. Senate and the President about the threats of climate change. The sea ice melting, glaciers melting, CO2 going up. And he says Paris is a complete waste of time. Now, I interviewed him Well, he gave a press conference, talked for about 45 minutes. Afterwards, was interviewed by many people. I recorded the questions and so on. Other people recorded questions that I asked, and you can see those appearing. But the point is, he's a scientist who thinks that nothing was accomplished, and yet other scientists are saying, "Oh, it's great. We got the ball rolling and stuff." So you're going to get a whole spectrum of views, and you probably have to form your own view. But I think it got people talking about climate change around the world. It got the Pope making a strong stand and doing an encyclical on climate change. It got world leaders, Obama and the Chinese government, talking about reducing emissions. China's promising to put a cap on their emissions by 2030. Probably not soon enough. I mean, I don't think any of the stuff at Paris is fast enough, especially if we're going to talk about losing sea ice in 5 years or something. But it got people thinking. So maybe, in another, I think what we need is a global fee and dividend, which is what Hansen thinks. And because that didn't happen, he says it's a failure. So anything less than a global fee and dividend, fee or tax on carbon, and then the dividend is returning money to people on a per capita basis. So in other words, the poor people they actually get money back, or 50%, 60% of the public would get money back under a fee and dividend situation. The people that would be paying the more for carbon are the heavy carbon users, companies and things. So anyway, whatever, you're going to hear all kinds of stuff on Paris. So please ask your questions, and I'll try to answer them. I can give you funny stories about Paris, anecdotes, or anything you want. I've been there once before. This is my first time in Norway, and it's just beautiful location that you're at, and there's access to the ocean, and we could put together a cheap prototype and get it out on the ocean and see how it works for some of the ideas of stimulating plankton growth, and and then there's all these fish that congregate around it. I mean, we've got loads of ideas for the company, so it's exciting stuff. And the Chinese say that crisis equals opportunity, and that's how we consider it too. So how are we going to questions with I guess we need the microphone. So, any questions so far? If not, I'll go around and I'll pick you out, and you can ask a question, right? So you might as well volunteer. It's easier.
One question.
Yeah.
If China got onto solar power, how would that affect the planet?
So the question was, if China got on solar power, then how would that affect the climate? Solar power growth is probably higher in China than just about anywhere else in the world. And it's funny, you can go on Google Earth and you can get locations. You can read something about a new Chinese solar installation going somewhere, and you can go on Google Earth and you can look down from above and you can see vast areas. There's a ruler in Google Earth. You can measure it. You can just see the Earth changing, and they have there's solar. The wind blows more the higher up you go. So any hilly areas, or if there's high rises or mountainous areas in China, you can see these from Google Earth, the satellite images, the recent satellite. You can see these installations going, and they're generating more and more power. Now they're up until recently. They were building a new coal plant in China every year. Every week there was a new coal plant appearing in China somewhere every week. And but see, the Chinese people are kind of rebelling because they're dying from the air pollution and the particulates that are coming. In fact, during Beijing Olympics, they had to shut down most industry for the entire Olympics, and they only allowed, they stopped people driving, I think, right in the main part. I mean, the air pollution is killing them. You can find, of course, any data you want just about on the internet. So if you Google global air pollution levels, you can come to a website which shows almost real-time air particulate pollution. And the safe zone is about 200, whatever the scale is, and there's cities in China that are 5,000, 4,000. Like people are literally dying there. I mean, their life expectancy is reduced by 20 years. Probably most people in those cities aren't even aware of that their life is being shortened by all the plants around. But so China has to address the air pollution problem, and they're finding, they don't want to build coal plants anymore. In fact, they're they're going to fade. They say that their emissions are going to peak in 2030. You know, I mean, it's good to have a target. That'll become 2020 in 6 months, right? And the ball has started to roll, and imagine if you take the example I give, take the U.S. military budget, 700 or 800 billion a year. Climate change is a threat to humanity on this earth, and you know it dwarfs all other threats. And take that money, and let's go to a renewable energy society, slash emissions. Let's put money in these ideas to remove carbon from the atmosphere. Let's put money in ways to cool the Arctic. And if we do that for a few years with the U.S. military budget, and on other military budgets around the world, we could solve a lot of problems. So, you know, how do we get to that? Humans react when our backs are to the wall. I'm saying our backs are to the wall. Most of the public don't think that yet, but I think they will soon. Especially if we have we look up in the Arctic from space, from a satellite, and there's no way there. It's all completely open ocean. I'll go to shorter answers. I'll try to make them maybe double the length of the question. So.
As much a statement as a question. Thank you for your interesting and frightening lecture. But
it's not fair that I'm the only one frightened. I'd like to spread the fright around everybody else.
I was born in 1938. 2.2 billion people. Today, we are approaching 7.7. That's maybe more of a problem than the greenhouse gases. And I would not put so much trust in the Pope in finding a solution. One thing more. You come from COP21. As most people suppose know, that this is an abbreviation for Conference on Parties number 21. My thoughts go back to COP1, Rio de Janeiro, 1992, presided by my fellow medical student, Gro Harlem Brundtland, who coined there that famous expression, sustainable development, Norwegian bærekraftig utvikling. And the combination of going down with the population and down with the GHGs must go hand in hand. What's your opinion on that?
That's an excellent question. I mean, population is the elephant in the room. I try to bring it up every climate event I go to. I was hoping somebody would ask me that because I haven't mentioned it this one. But we're 7.3 billion, and we're heading up about 1.2, 1.3, 1.4% per year. We have exponential growth in population, and obviously, this can't continue long term. Abrupt climate change, the changes that are coming down the pipes if we lose sea ice. I mean, we do have they'll threaten global food supply. So if food prices double or triple, we do have a bit of a buffer because about 30% to 40% of the food that we grow ends up in the garbage. It's mostly not in Europe, of course. It's mostly in the U.S. I mean, serving size in restaurants, and they pour water, people don't drink. But we do waste an awful lot of food, and people talk, a lot of the meat that we eat. I mean, what's happening is, so population is increasing exponentially, but also people are aspiring to more and more, eating more and more meat in India and China, and consuming more. So consumerism, the effect on the planet is the consumerism times the population, and it's like, as you say, I mean, it's just not possible. I mean, it's interesting because the Club of Rome in the 70s said that population would not grow much more because we were going to run out of food. We couldn't sustain the population. And what happened we managed to, in about a decade and a half, we managed to increase the amount of food we could get from 1 hectare of agricultural land by but we doubled it, and we doubled it again, with different irrigation, grafting techniques, and becoming smarter at farming. And we increased it about 20 or 30 times. And so the Club of Rome was completely wrong. They didn't foresee any of that. I mean, how would you? But the point is, we have to do something about population. We have to have all these important issues we can't just ignore. Like we can't. I agree completely. We can't just. I mean, a lot of climate change is an energy problem. You know, and the amount of energy that society uses depends on how many people there are, right? And we can't keep growing and growing and growing while the biodiversity on life is shrinking and shrinking and shrinking. Right? We're losing creatures, and we fished out 90% of all the large fish in the ocean. Right? What about that last 10%? Luckily, the lower, the whales didn't go extinct not because we decided to stop killing them and hunting them. They're still around because there became so few of them that it wasn't economical to continue killing them for whale oil. So that industry died, and then that allowed the whales to start coming back. So we do a lot of things that happen accidentally. Like we haven't planned. When you cut down a forest and grow crops, you don't think, well, we've changed the reflectivity of this region of land from space, and we're growing canola, which is really light and reflecting a lot more energy, so it could cause a cooling. I mean, we don't consider the climate impacts of what we do, and we need to consider the climate impacts of everything we do on our scale on the planet.
I learned when I was younger that the ice period goes, and that's happening after the heating of the earth. First warm, and then you get a new ice period. And the Gulf Stream, if the freshwater press the Gulf Stream more and more to the south, then it will maybe make a new ice period. Is that correct?
Okay, so the Gulf Stream carries tremendous amounts of heat across the Atlantic, and it keeps Western Europe at reasonable temperatures. It makes Britain fairly warm compared to if you compare European cities at a certain latitude to Canadian cities at a certain latitude, the Canadian cities are much colder at the same latitude, and the reason is because about a third of the heat that comes over from the Gulf Stream keeps Europe warm. So if the Gulf Stream shuts off, then yes, there will be regional cooling of Europe. But in the past, the Gulf Stream has shut off. The ocean currents have shut off at times in the past, and we've gone into cooling. But the warming so there'll be a lot of turmoil sort of on a regional basis. But we've changed it. The atmosphere traps a lot more heat. We've changed the chemistry of the atmosphere. It traps a lot more heat, and then that effect is far stronger than say a Gulf Stream shut off causing a global cooling period in the northern hemisphere. In fact, the natural ice age cycles of warming and cooling because of the change of orbit of the Earth around the Sun over long periods of time that's caused previous ice ages and warm periods and ice ages. We've disrupted that cycle. It's almost a certainty that we would not go into another ice age. That the chemistry of the atmosphere would keep us from going into another ice age. I mean, we wouldn't be due anyway. If we hadn't affected the atmosphere like we have, we would be in a cooling period right now. But that's completely overrun by the CO2.
No. Yeah, I used to work for mobile oil and Statoil in the North Sea. And on Sleipner platform, we took all the CO2 from the sales gas and re-injected this water filled reservoir. Is it possible to take CO2 directly out of the air and re-inject it?
So there's a couple major projects in the world to look at that, and it's called it's carbon sequestration or carbon capture and storage. So you capture it from the air and you put it back in. So Statoil has they have put the most money and have the largest project to do that. But Canadian government has done a similar thing in Weyburn, Saskatchewan, they have a plan. Now, these ideas were advocated by the fossil fuel industry because it was a way that they thought they could justify and continue to run their industry and be doing a good thing to be capturing it. But the volumes required are very, very small. So if you had to capture all of the CO2, you would need an enormous, like it's much beyond the scale of anything that we've done. So these plants, they've taken a tremendous amount of money that could have been going into renewables and some other areas. I mean, I think people are coming to the realization, even in governments and in companies, that that method is probably not the best way of doing it. It's not the easiest way to get CO2 from the atmosphere. I mean, what's the easiest way to get CO2 from the atmosphere? Stop cutting down the forest that absorbs a lot of CO2, right? Plant trees everywhere, and try to increase the amount of CO2 that goes back into the ocean by, for example, the plankton idea. I mean, iron is a nutrient in the ocean that is very limited. So this rogue guy started this, he put iron off the west coast of Vancouver, 200 tons of iron into the ocean. And it was kind of approved by one of the First Nations of Canada people on one of the islands, and they kind of said, yeah, it's okay, this is our fishing area, go ahead. So he did this. And it caused tremendous phytoplankton growth you could be seen from space. And the next 2 years after that, there were record salmon runs. Like the salmon runs off BC were dropping, and then they spiked up to higher than they had ever been in about 40 to 50 years. And that lasted for 2 years. And some scientists from the government are still saying, well, we can't really relate it to the iron, to the plankton, but it's pretty obvious that it was the plankton from that. So, the risk is that we do things and mess things up even more, right? And who gets to decide whether you do some of these things, right? So these are all things that are like, is it some government that does it? What if you, like, we know that the Earth will cool when there's a volcano. A big volcano like Pinatubo will cool the planet 0.5 degree for 3 years. An even bigger volcano in 1815, it caused a year without a summer in North America. It cooled the planet about 1 degree Celsius for 5 to 10 years. And it's because of the sulfur dioxide in that volcano. So we build coal-burning power plants that put up sulfur dioxide into the lower atmosphere. Like coal that has a lot of sulfur content, depending on the purity where the coal is mined. And if it's low-grade coal, it's kind of brown coal, then a lot of sulfur comes up. So if we take that sulfur that nobody complains about it going into the lower atmosphere, although they did with acid rain, right? And they tried to scrub it out. But if we put that same amount of sulfur from one power plant into the stratosphere, then the particles there reflect sunlight and can cause a cooling. And yet nobody wants to talk about this even because it's a very controversial idea. Well, don't talk about it. But if you say you're against it, I'm completely against putting sulfur into the stratosphere because call it geoengineering, which is a term people hate. Then say, okay, if we don't do it, we're going to have extreme weather events increase 10 and 20 times. We're going to have cities flooded out. We're going to have tremendous infrastructure damage, billions of dollars. Look, we need to look at what happens, the pros and cons, right? You can't just say that I'm against this technique. If it kind of stabilizes climate for a few years, give us a bit of time to drop fossil fuel emissions. So, I know tonight you're probably hearing a lot of things that you haven't heard before, you're not thinking about, but I wouldn't give this talk if I wasn't convinced that these things are coming in the very near future for all of us. So, we're better prepared to understand what's going on, from what I'm trying to tell you.
So I'm going to put you on the spot and ask you a localized question. And the localized question is, based on the projections that you're looking at globally, is there any particular way that people in Norway generally, or in a place like Kragerø,
can anticipate or think about what are the implications locally if these broader issues were to come into play. So, for instance, we mentioned we're on a coastline, and we talk a lot about, and we hear a lot about sea level rising, but that isn't even across the world. So, what and how can people in Norway or in Kragerø determine, well, what could be like here? And we're looking at whether that will come to the question, for instance, about regional cooling at the same time that you get overall heating. Is there any way that people in this part of the world can actually see and anticipate what might happen here?
Yes, very good question. This was asked of me in, I guess, February of this year by an NGO, non-governmental organization called Manitoba Wildland. And what they did is there were some hearings coming up with the Manitoba government on Lake Winnipeg. And they said, can you do, I've seen your stuff on the internet. Can you take the global stuff and go down to the local Lake Winnipeg watershed level and tell us what's going to happen and testify at these hearings? So I did a 50-page report, and I did PowerPoint slides, and they gave me an honorarium after a couple thousand Canadian to do it. And I testified to the Manitoba government, told them exactly what was going to happen globally and how it would interfere, how it would affect the local thing there. So I could do that for anywhere in the world. So I could say, okay, what's going to happen here? Right? I could look at the data on sea level and try to bring it down to the local level. I could look at the data on climate variability. I could take the 30-year averages of climate in this region, and I could look at what's happening now. The point is you could get a meteorologist to do this, or you could get somebody else to do it, and what they're going to do is say, well, there's a 1 in 200 year chance of a flood, from the river here or whatever, and they're going to base this on the last 100 years of data, and that doesn't mean anything because the statistics have changed, right? The climate has changed, so the statistics has changed. So a 1 in 200 year, a 1 in 500 year flood, it doesn't mean anything. Those numbers are wrong, right? I mean, if a 1 in 500 year flood happens 3 times in 10 years, obviously something's messed up. So what I could do is take the knowledge I'm talking about globally, like what happens when if we lose sea ice in the Arctic. Then the whole Arctic region is going to get a lot wetter, right? It's going to get a lot warmer. The ocean temperatures are going to be a lot warmer. It's going to get a lot wetter. It's going to be a lot more water, like precipitation and water as opposed to snow. The jet stream patterns will change, so it'll cause, and you won't get any snow in Norway in the whole winter, right? It won't snow here at all, right? Maybe you can start growing, putting palm trees up. I'm not quite, I'm joking about that. Palm trees and banana trees. I'm going to try that in Canada. Right? I mean, things are changing. There's a guy in the Arctic, north of the Arctic Circle, he's growing potatoes. Right? He has a little bit of he put plastic sheets up, to keep the wind on when it gets super cold. He's growing potatoes. It's tremendously expensive to ship food up to the northern Canadian Arctic to supply some of the small cities, small towns there. So, but they're starting to be able to grow their own food. So, we're pretty adaptable species, right? We do stuff like this, right? So I could look at any region and do an assessment like that. So, if you're willing, if you want such a thing done, then you have to, encourage me to do it. So, I have send donation or something and say, I want a study done on this city, and then, I can put something together, right? Or talk to Nude, do it through Nude. I mean, one of the things is a company, to get us going. We could start doing some regional reports, and I could consider all the aspects. You have a loud voice.
Yeah. I just want to say, speaking on local things, I just want to tell a very short story from here. Because
we have one very clever guy in Kragerø called Paul Beckwith, and a few months ago I was talking to him, and I talked about geoengineering, which I've been obsessed with for like 10 years, and he said, And it's kind of Frankenstein technologies in a way. It's like you put a lot of sulfur dioxide in the atmosphere, you have mirrors out in space, or you have these synthetic trees, and I really don't like it. And then I read these books by James Lovelock, and it's a GAIA theory that Mother Earth, is a living system. And I talked to Per Erik, and he said, like, you can't talk about geoengineering because it's a poisonous word. Nobody will take you seriously. You have to come up with another word, and for your new technology, because I was talking about green technology that was in harmony with Mother Earth, but environmentally friendly ways of cooling the Earth and taking out carbon out of the atmosphere. And Per Erik said, that won't fly. Get a new name, otherwise forget it. And I said, okay, how about GAIA engineering? And he said, yeah, that might work. So here we are with GAIA Engineering AS, local Kragerø company. Thank you.
If you think that you're not being affected by climate change right now too much, then look at what's happening to the economy of Norway and the economy of Canada. Okay, Newt tells me there's 300,000 people that are working directly in the oil industry in Norway for the offshore oil. In Canada, there's probably a similar amount. In fact, there were labor shortages. So what they did is they get people from Newfoundland, big tough guys from Newfoundland who worked on the oil rigs offshore, and they offer them, a couple 100,000 Canadian a year, and they fly them to the oil sands. And they stay there, they work every day for 20 days or something, and then they fly them back to Newfoundland. So there's charter planes to carry these people across the entire country back to Newfoundland for 10 days, and then they go back for 20 days. And how is it, like, when they talk about carbon in the oil industry, they don't consider any of that, of course. But the point is, when it got so out of hand that people couldn't live anywhere in the oil in Fort McMurray, like rents were so high, properties were so high. So even though these people were making, you drive a truck, one of those huge trucks that, make me 150,000 Canadian a year, but you're paying a third of that on accommodation for a little tiny apartment, and the person, you go to McDonald's there, and the person's making $30 an hour at McDonald's because nobody will do it for a lower price, and it just screws everything, and then the crime rates go up there and stuff. So when the oil was $100 a barrel, the Canadian dollar was about 92, 93 cents compared to the U.S. Okay, oil's dropped to about 40. And the Canadian dollar has dropped to 75 cents. Now, oil's slipping under 40. It's 39, 38, 37 a barrel. And the Canadian dollar is now about 72 or 73. Now, some are saying that the oil industry thinks that the price is going to recover. We're going to be 100 again. Everything's happy. We continue on. There's demand destruction is occurring around the world. More and more universities, more and more companies are saying we want to divest from pension funds, divest from oil. So this is happening. So we don't know that the price is going to go back up. So the Canadian, I expect, the Saudis, whoever produces oil in the world the cheapest is gonna try to sell their oil and get the money for as long as they can. And this is Saudi Arabia. They can still get it out of the ground for cheaper than anywhere else in the world. So they can destroy all the competition. And when the last barrel of oil is sold, we'll still be using oil for creating chemicals and plastics. Maybe not plastics. We're doing that with biomaterials, but we need to change our way of thinking on this. Canada is in a lot worse shape than Norway because Canada had no foresight. There was supposed to be money from the oil industry put into this fund. The Norwegian Sovereign Wealth Fund is $1 trillion. If the oil industry completely collapsed, the government could take that trillion, divide by the 5 million people in Norway, everybody's a multimillionaire, right? Everybody's a millionaire, and then you can start doing other things, right? Canadian government has almost no money in this, so we're in a lot worse shape. If oil drops to $20 a barrel, then the Canadian dollar will be 60 cents or lower compared to the U.S. dollar. The kroner is doing the same thing. I think it was worth a lot more when oil was $100 a barrel, and it's a lot lower now. And as oil continues to fall, it's going to continue to fall. So what we're talking about with this company is what can we use? What skills do those 300,000 people that work in the oil industry in Norway have? You know, they have a lot of skills with machinery, heavy equipment. So we're trying to find ways that the ships and the people, the personnel, can be used to extract a lot of CO2 from the atmosphere, right? With some of these methods that you can get more information from us on. And the same thing with the Canadian oil sands will be one of the first to drop off the map. I mean, coal's being destroyed right now globally, right? Coal is on its way out. The major U.S. coal companies have lost 95% of their value in the last few years. And Australia is in deep trouble because their main industry is coal. So the Australian dollar dropped even more. So, you know, things are changing. I mean, you can either try to figure out what's happening and adapt, or you can just ignore it and climate change, and then stuff's going to happen that you completely that completely shocks you, right? I mean, we're always shocked when something non-linear happens. I mean, but the world is non-linear. You know, bend a stick and it bends a little bit, put more force, it bends a bit more. Suddenly it snaps. Oh, we're surprised. You know, it snaps. You can't go back. You can glue it together, but you know, so we're pushing on the climate system so much that if it snaps, we're not going to be able to go back to where we were. So we're talking about humans being the biggest impact on the climate system. And if we get smart about it, then we can try to bring it back to stability and so on. But we can't ignore things like population. And we have to talk about all of the factors and not ignore things. So if we ignore things, we get into trouble that way. So I say, you know, 700 billion, 800 billion a year. You know, let's take all those engineers that are building weapons to kill people in the U.S. You know, and let's figure out how we can, you know, make a more stable system. I mean, it's utopian maybe, but I think like it will eventually happen. Imagine a big hurricane taking out New York, for example. Imagine sea level rising a couple meters in 30 years. If you take the present rate of melt from Greenland and Antarctica, and if that doubling rate continues, then we're talking about you can take a napkin and you can say, okay, Arctic, Greenland and Antarctic ice melt doubles every 7 years. Okay, so the doubling rate is every 7 years. So take 7 years, it's double. Take another 7, it's double. Another 7. If that continues, we're talking about 5 meters or 7 meters of sea level rise by 2070. Right? So is it going to do that? Is it going to continue doubling? Or, we're talking about huge effects on humanity, right? It's just like, so anyway, any more questions or? So,
I think you said something about before the break we had that we would cool the Earth down so fast, faster than we actually heat it up right now. Would that mean that we could continue as usual?
Okay, if you Google, I did this blog 3 years ago. I called it Anthropogenic Arctic Volcano. Okay, I said we put sulfur in the Arctic, create sort of like an artificial volcano, and we can calculate how much sulfur, and we could simulate like a major volcano, and we could cool the entire planet a degree for 5 or 10 years. Right? So, but the problem is this could buy us time. Like we're going to get into a worse and worse situation if we keep the emissions of fossil fuels going way up, because we've changed the chemistry. We're going to continue to change the chemistry of the atmosphere and the ocean. And if we use this way of, so if we injected huge amounts of sulfur dioxide into the stratosphere over the Arctic when summer comes, we would cool the Arctic significant amounts, right? But it does nothing for ocean acidification, for example. So the CO2, it does nothing for CO2 levels in the atmosphere or the ocean. And CO2 levels will continue to rise with our emissions and the ocean pH. The CO2 in the ocean makes the ocean more acidic. And if it becomes more, passes a threshold, then sea creatures like phytoplankton, diatoms, coproliths rather, they have a calcium-based shell. They can no longer form their shell. So it changes the physical nature of the phytoplankton. We don't have oysters, we don't have clams, we don't have lobsters. They can form any of their shells at the lower pH, at the higher acidity. So that's why we need the carbon dioxide removal as well. So there's been the idea of this three-legged stool has kind of gelled with me over the last 4 or 5 years. I was completely against any modification techniques, called them geoengineering techniques, until I realized that if we don't do it, we're in a far worse state. So then we need to look at what we can do with the least amount of risk. We change the atmosphere, the chemistry. We can change it back, right? So, isn't that a good thing if we could figure out a way to do that and apply technology that, all the people working with, in military or oil or some of these industries that cause harm to the atmosphere to correct, the same people to extract CO2. We have to provide guidance. Government has to provide guidance. Say they don't tell people how to do it. They tell people we have to lower CO2 levels to 350 parts per million. Here's $300 billion, right? And we need to do it as soon as possible. So, don't you think the engineers around the world that are designing sophisticated, space, like rockets and weapons and this and that, don't you think some of them might have some idea? Just need one person to figure out a good way of doing it that can be scaled up, and we can lower the levels to 350. That's why I don't, there's more and more people, there's Facebook groups where they're called near-term human extinction, right? There's people, I won't mention any names, there's some guy going around giving talks around the world saying humans are going to go extinct by 2030 or 2040. How is that possible, right? I mean, there's a lot, there's despair. I mean, what kind of hope? I made a joke to these people. I said, after COP, a lot of them are upset saying COP's a waste of time. I said, no, COP is great. Paris is great. I said, the reason you don't like it is because you thought you didn't have to worry about a retirement savings plan. If you thought the world was ending in 30, spend all your money now, just go out and party, enjoy yourself. You don't have to save for retirement. You don't have to worry about, your kids' education or anything. We've only got 15, 20 years, so you don't need to save anything, right? Just go, it's great, So when they realize that, hey, we might be around for a bit longer and they haven't saved any retirement or whatever, they're upset, right? Like the stock of tinfoil hats and sandwich boards will plummet, right? We may have solutions, right? So it's important to, I'm saying, on some of these groups, there's 2,000 to 3,000 people in a Facebook group, and they think that the world's coming to an end in 10 or 15 years. I mean, how depressing and doomsday was that? But I mean, there's more and more. Kerry, in his speech a couple of days before the end of the COP, said, this climate change is the biggest threat humans have ever faced. It threatens their survival on this planet. So, when you talk about these other people in these groups, I mean, they're, maybe Kerry will start joining one of these groups. But I'm not gonna. I think that we are resourceful enough. We have to recognize the problems. Their backs are against the wall, and we have to find solutions. So this is what the company is about.